Okay, so welcome to the new lecture of the course Fundamentals of Solar Photovoltaics and Technologies. So today in this lecture we will cover the topic starting from materials for solar photovoltaics, starting with semiconductors. So in the previous few lectures we talked about solar radiation, that we get a lot of energy from the sun which is intercepted by the earth, and amount of energy that we receive on a given location depends upon the coordinates, that is longitude, latitude, and the ambient conditions, which are quantified in terms of air mass, but are dependent upon things like cloud cover, humidity content, and other things in the atmosphere. Typically, we characterize the radiation, standard radiation for photovoltaic devices, especially in terms of measurement, as AM 1.5 G, where G means global, and AM 1.5 is sort of the average of solar photovoltaic energy, that solar energy that you receive during the day, and this is basically 1000 watts per meter square or 100 milliwatt per centimeter square. So this curve at the bottom shows that solar irradiance varies as a function of wavelength. It peaks in the visible region, and there is a substantial drop in the intensity of this irradiance once we receive the radiation at the sea level, which is because of absorption losses in the ambient. And part of the spectra that we are interested in for solar cell application is basically from about 250 nanometers until about 1000 nanometer. This is the region in which we operate for most of the solar cells. So as a brief recap, we understand that solar radiation that falls on the earth is abundant. It has a very large number, and this is sufficient to meet our energy requirements in principle. The changes in radiation occur because of atmospheric effects and also because of time and position of the surfaces with respect to horizontal. We also learnt about the geometry of the sun with respect to the earth, and the location on the earth to exactly determine the amount of solar radiation flux that we get. And this intensity of radiation that falls either per day or per hour can be worked out through empirical relations, and it can also be measured using certain equipments like pyranometer and pyrheliometer. And there is a reasonable consensus between the measurements and the calculations, and so this allows us to quantify the solar radiation. So next our discussion will be on semiconducting materials, the materials which form the backbone of solar photovoltaic devices. So for semiconducting materials, I would like you to understand the basics of solid state physics. We will cover that aspect in a very fast forward manner, but if you wanted to build your knowledge in the area, then I would recommend these books: Electronic Properties of Materials by R.E. Hummel, especially chapters 1 to 5, Solid State Physics by Charles Kittel, especially chapters 1, 2 and 7, Semiconductor Fundamentals, volume 1 by Robert Pierre, and Advanced Semiconductor Fundamentals by Robert Pierre this is volume 6. So these books, especially the first 2 or 3, will help you build the basics of the band theory and its consequences in terms of materials. Band structure that will be very helpful. So the solar photovoltaic technologies have evolved in 3 stages typically. So we call them as generation 1 technologies, which developed in 1950s, and they are primarily based on monosilicon and gallium arsenide, and they are based on the wafer of size or thickness 0.5 millimeter. And 70s and 80s, a lot of work was carried out on thin film devices which reduce the amount of material that we use. They are based on polysilicon, thin films of cadmium telluride, copper indium gallium selenide, amorphous silicon, which use the materials, the main light absorbing material, to be around 3 to 5 microns. And then in generation 3, with the exception of dye sensitized solar cells, materials such as organic materials including polymers and small molecules, perovskite solar cells, quantum dot solar cells, multi-junction solar cells of different types, which use materials even in smaller quantities, thickness is less than 1 micron. And this is how the whole evolution has taken place. So the first generation was based on thick wafer based solar cells of about 0.5 millimeter. Now it is about 0.3, 0.2 millimeter thin. Generation 2 were based on thin film technologies of around 3 to 5 microns with and these thin films were mainly physical vapor deposition or chemical vapor deposition processed, and in the generation 3 devices we focus on solution processed materials whose thin films are less than 1 micron. The core of these materials which are written on the screen, whether it's silicon or gallium arsenide or cadmium telluride or copper indium gallium arsenide or polymers or perovskites, all of them have one common attribute, that they are all semiconductors. So we really want to understand what are semiconductors and what are typical semiconducting properties which are important for solar cell applications. So before we move on to semiconductor, let's just briefly see what are the materials that we require in a solar cell device. At the very simplest, a solar cell device will consist of a p-n junction, typically a p-type silicon wafer. On top of that we have an n-type silicon region, and at the very simplest it will have contacts on two sides, one on the back side, one on the front side. If the light is coming from the front side, then the front side needs to be able to absorb the light. As a result, the front contact has to be digitized, or it has to be put in the form of thin lines or thin grid in such a fashion so that they do not block the front surface. So that is why you will see on silicon there are thin stripes of metal which are put on top. Back side, if it is not an absorbing surface, then it can be completely coated with the electrode. So basically, first thing a solar cell device needs is an energy absorber, and this is typically energy absorber, meaning that the one which can absorb the solar radiation and convert that solar radiation into required power or electrical power. So typically we use a semiconductor for that, and in most devices in the form of a p-n junction. So we need to understand what a semiconductor is, and secondly, a solar cell device uses contacts which are basically metals, and these metals are there to extract the carriers which are generated upon illumination. And the important thing is the side which is illuminated needs to have transparency. So as a result, configuration of contacts on the top side or the side from which light enters, it needs to be it is very important. So it has to be either transparent or it has to be put in the form of a grid so that maximum amount of light can be absorbed. So this is where we use a top contact, which is either a transparent electrode such as indium tin oxide or fluorinated tin oxide, or a grid of, let us say, silver, okay, so that maximum light absorption can occur. In modern devices, there could be presence of other layers which are inserted to provide certain advantages, such as silicon surface is very reflective. As a result, sometimes in most devices on top we put a anti-reflection coating on top. So you will see that on top we also have a thin anti-reflection coating. So this layer could be anti-reflection coating. On the back side also sometimes a layer is put to improve the carrier extraction or device characteristics. So depending upon the device configuration, in organic and perovskite solar cells we put electron and hole transport layers on top of the bottom of the semiconductor. So depending upon what kind of device you have, between the metal contact and the semiconductor there are other interlayers which are present. So basically a solar cell device is a multi-layered structure. So we might have a semiconductor, on top of that there could be other layers, and all these layers have to be transparent to light, by the way. So there could be layer 1 here, there could be layer 2 here, and then on top we can have contacts, and on the bottom we can have contacts. So depending upon what the device is, you will have at least 4 to 6 layers in a solar cell device, and they all have different functions. But the key thing is that the side from which light enters should provide maximum transparency of all the layers included, so that radiation can be absorbed by the semiconductor. So that is why there is a need to understand materials so that you can choose appropriate materials, because it's an electrical device. As a result, the electrical what we call as energy bands, the alignment of energy bands with respect to each other is extremely important, and that is why you need to understand the bands and materials. So this requires you to understand energy bands in the material and how they align with each other when they are put in a device. And this is where we will also learn what is the difference between, for example, a metal and a semiconductor. So these are some aspects that we need to learn. The material requirement is, first, for a solar cell device, the light absorbing material must be a semiconductor. So for absorption of, so for light absorption, and this must have an optimum band gap. Around 1.4 electron volt is the band gap that we seek, but many materials do not have this band gap, but so we operate within a range. Generally the range could vary from 1.1 to 1.6 electron volt depending upon the type of material. The semiconducting material must absorb the light as much as possible within wavelengths 300 to 1000 nanometer, which is the visible and regions near the visible region. The surface reflection should be minimum. If it is not low, then we need to find methods to minimize the surface reflection. The material must have good charge transport characteristics, so that charges, when they are created in a device, they are moved swiftly or without much loss to the electrodes, and they must be collected at the electrodes efficiently. These are some of the requirements that we must fulfill to choose the material, design the device appropriately, and this is where a lot of emphasis lies on a lot of understanding of material selection, device design, how they are put against each other, where they are put against each other, material and device fabrication strategies, and electrical engineering to minimize the parasitic resistances. So knowledge of all these topics is required in order to make a good quality solar cell device. So the questions that we will address in next few lectures revolve around, first of all, what are metals, semiconductors and insulators. We define what are metals electrical properties, namely conductivity and resistivity. We also introduce a concept of what we call as in this process Fermi energy. And then we will look at the formation of energy bands in materials in a very fast forward qualitative manner. We will not do too much of mathematics around it, and then we will look at semiconductors, especially looking at what the direct and indirect band gap semiconductors are. So these are some of the questions and the questions around them that we will address. So the first question is, what are semiconductors and how do they differ from metals on a very general basis? So if you look at broad categorization of electronic materials can be categorized on the basis of a parameter called as electrical conductivity, which is ease of electrical conduction in the material. So you can see that this conductivity on a scale of per ohm centimeter or Siemens per centimeter varies on the far left from 10 to the power minus 22, which means very low electrical conductivity, to very high electrical conductivity such as 10 to the power 6 ohm centimeter inverse. So on the very far left end of the spectrum, we have materials which are called as insulators, which are not very good electrical conductors. So things like plastics and ceramics, many plastics and ceramics, they will fall in this range, which will have conductivities varying from 10 to the power minus 10 to 10 to the power minus 22 ohm centimeter inverse. And materials like glass or alumina or magnesium oxide, many of these oxide materials which are highly insulating, which are ceramic materials, or plastics, many plastics, they fall in this range. You can see that is why the electrical sockets are made of either ceramics or plastics. Then we have a range from 10 to the minus 3 to minus 10 ohm centimeter inverse. This is where semi insulators form. These are not exactly heavily insulating, but they are quite insulating. And somewhere between 10 to the power minus 3 to 10 to the power 4 ohm centimeter inverse, we have what we call as semiconductors. These are the materials which are semiconducting. They are not highly insulating. They have properties which make them attractive for semiconducting applications, semiconductor device applications like silicon, gallium arsenide, etc. And the materials also that I listed above in the previous slide was cadmium telluride, copper, indium, gallium selenide, organic conducting polymers, not the normal polymers, but conducting polymers. Typical polymers will be here, they will be plastics, polymers, or resins, thermosetting polymers. So, they will all be in the plastic category, very insulating, but there is a special class of polymers which are organic polymers, they could be conducting. And then we have recently being researched a lot perovskite materials and many other materials which are semiconducting, whose resistivity, electrical conductivity lies from 10 to the minus 3 to 10 to the 4 ohm centimeter inverse. And then on the far right end we have metals which are heavily conducting. That is why we have all the electrical wires made of metals. Typically they are made of copper, they used to be made of aluminum, but other metals such as gold or silver, even some of the ceramic materials like indium tin oxide. Indium tin oxide is InSnO2. So, basically you can say it is indium doped tin oxide, okay. And this is what makes it conducting. And there are other examples such as fluorinated tin oxide. So, you can have FSnO2, these are also conducting materials. So, these are conducting materials which allow the conduction of electricity in a very swift and efficient manner. In between we have semiconductor which are somewhat conducting, but not exactly to be used as conductors or especially as wires or other metallic conductors. And then on the far left we have insulators which are highly insulating, and you can actually, they will not transmit any electricity at all. So, the parameter is electrical conductivity, which is defined as sigma. Sigma is equal to Ne square tau divided by m. So, where n is number of electrons per unit volume, E is the electron charge, tau is what we call as relaxation time, and m is called as mass of electron. And this expression is valid for most materials. We can also write this as Ne mu, where mu is called as mobility, which is a very important parameter for carriers, and this can be defined as E tau divided by m. Okay. Inverse of conductivity. So, this sigma is conductivity. Inverse of sigma is called as electrical resistivity, which is m divided by Ne square tau. So, basically you can say this scale is on electrical increasing order of electrical conductivity or decreasing order of electrical resistivity. So, naturally the units of resistivity will be ohm centimeter and units of conductivity are ohm centimeter inverse. So, this parameter electrical conductivity or electrical resistivity is extremely important in defining what a material is, whether it is a metal or semiconductor or insulator. So, conductivity of a metal is defined by sigma is equal to Ne square tau divided by m, where n is number of conduction electrons, the electrons that take part in conduction, tau is relaxation time, m is mass of electron, and E is electronic charge. So, basically there is energy. So, if you, I am going to fast forward lot of things, but quantum theory says that there is energy level called as EF. So, if on the y axis we plot energy, on the x axis we plot energy, on the y axis we plot probability, let us say Fe, then I can plot this function. This is a function which revolves. This is half, probability starts from 0 to 1, and at the midpoint it has half probability. So, it is the electrons which are in the vicinity of EF at a temperature greater than 0 Kelvin that conduct. So, basically at 0 Kelvin what happens is that in metals also at 0 Kelvin, probability of energy levels being filled is 1, and at 0 Kelvin none of the energy levels above EF are filled. So, sorry, should be up to this point EF. So, this red curve is at 0 Kelvin and the blue curve is at a finite temperature more than 0 Kelvin. So, basically this EF is a very important number which tells you the threshold of energy around which carriers are excited, and this is a threshold of energy above which no energy level is filled at 0 Kelvin. So, all the energy levels are filled at 0 Kelvin below EF, and this is called as Fermi energy. Fermi energy, and this equation is given as 1 Fe is equal to 1 over 1 plus exponential of E minus Ef divided by kT. Okay, we will look at this equation again, but this is what it means, that number of electrons which are in the vicinity of Fermi energy conduct, not all the electrons which are present in the metal, which was assumed earlier and it was proved to be incorrect. So, the classical model that was used for metals was that all the electrons take part in conduction, and people worked out various formalisms, but it turned out the classical theory that was used for metals does not explain semiconductors. For example, first departure was temperature dependence of conductivity. Metals generally show a decrease in electrical conductivity with increasing temperature, because as you increase the temperature, this factor tau, which is relaxation time, the average time between two successive collisions among the electrons, tau decreases as temperature increases, because as you increase the temperature there are more thermal vibrations within the metal. As a result, there is more scattering of electrons. So, the relaxation time goes down as the temperature goes up, because the electrons in a given core of, let us say this is your solid, electrons are moving like this and they undergo a lot of scattering as temperature increases. So, what was observed was that metals show a decrease, metals and this should be dependence, metals show a decrease in conductivity with increasing temperature, but semiconductors on the other hand show an increase in conductivity as temperature increases, at least in certain range. So, here you can say sigma decreases as temperature increases, here sigma increases as temperature decreases. So, what is the as temperature increases, sorry, not decreases but increases. What is the reason behind this? This could not be explained using the quantum using the classical theory of conduction, where you considered that all the electrons take part in conduction. Another was sign of Hall coefficient. Hall coefficient could be positive or negative, which suggested that it is not just electron that take part in conduction, it is also another charge that takes part in conduction. So, this means that only electron model does not work. So, you have to have electron which is a negative charge, but you also have to have positive charge, which later was called as a hole, that also takes part in conduction, and this could not be explained by classical theory. Third was existence of band and band gap, that materials, as we found later, they have energy bands. So, they do not have continuous energy. So, if you plot energy of energy, then you do not have states which are continuous energy states. They are not, there is no energy continuum, rather you have discrete energy states as quantum mechanics showed. So, this, and fourth was specific heat behavior at low temperatures. The specific heat which was measured was much lower than what was predicted, and this requires one to go to quantum mechanics. So, this is how quantum mechanics birth took place, and quantum mechanics invoked certain physical explanations which helped us understand, which helped us migrate from metals to semiconductors in a seamless manner, and which also helped explain many physical phenomena that we observe, which are otherwise refuted by classical theory. So, electron was typically considered as a particle earlier, but de Broglie suggested that electron in any material does not act only as a particle, it also acts as a wave. So, wave particle duality of electrons hypothesized by de Broglie, who was a French scientist. He connected the wavelength of electron. So, he considered electron as a wave, which means it must have a wavelength, and the momentum p, which is shown by a particle. So, he connected these two and he said lambda dot p must be equal to h. H is Planck's constant, or p can be written as h cross k, where h cross is h divided by 2 pi, and k is called as wave vector, which is related to wavelength as by 2 pi divided by lambda. So, you can see that wave vector here is a inverse. So, the unit of wave vector is centimeter inverse or meter inverse. It is inverse of wavelength. So, these two, so one can connect the momentum and wavelength or wave vector, because momentum is a vector. So, wave vector is also a vector, whereas lambda is a scalar quantity. So, we treat this in a vectorial fashion such that p is equal to h cross k, and this is what is a very important relation that was hypothesized to connect the wave particle behavior of electron. And this was also proven by several experiments. For example, electron moves like a particle, but it also undergoes diffraction. And diffraction is a wave phenomena, right, which is a wave phenomena, and this experiment was conducted. So, it was proven that electron in a solid moves like a particle, takes part in conduction, but it also displays a wave like behavior, it undergoes diffraction, and that is one of the reasons why we have band gap in materials. So, this wave particle duality was a very fundamental turning point in moving from classical behavior of electron, where they just behave like particles, into a more like a combined theory. So, basically wave particle duality was hypothesized in 1924 by de Broglie, and wave nature was proven by Davison and German electron experiment, diffraction experiment in 1928. Just like you see diffraction of waves using simpler Thomas Young's kind of experiments, he proved, Davison and German, they proved that electron diffracts when it interacts with periodic solids, and there is a diffraction pattern. And finally, in 1926, this was all combined and put together by Erwin Schrödinger in a mathematical form in 1926. So, basically, if electron was to be considered as a wave, it must have wave-like properties, which means it is a wave which has a disturbance which is periodic in space and time. It should have properties like wave velocity, wavelength, frequency, and wave number. It also is characterized by a quantity called as wave function psi, and this is a very important property which allows one to analyze the behavior of electron accurately. It also follows Heisenberg's uncertainty principle that both position and momentum cannot be determined precisely simultaneously. So, delta p and delta x must always be greater than or equal to h, and probability of finding electron anywhere in the space is psi star. Psi star is the conjugate of psi multiplied by the volume, that is dx, dy, dz. So, we will stop here. So, this is what is the foundation of quantum mechanics. From here, we will talk about the solution of Schrödinger equation in very simple cases and see how can this be taken forward in the context of electron in a solid to give rise to bands and band gaps in the materials. Thank you.